Hello lovelies, in this paper the brilliant Charlotte's going to be taking you through my AS Chemistry paper 2 for OCR. So what I want you to do, if you haven't had a go at the questions already, is look at them on screen, pause the video, try and answer it for yourself and then play and go through the answers to Charlotte.
Hi everyone and welcome. Today we're going to have a look at this AS Chemistry for OCR. It's a paper 2 depth in chemistry paper and it is your predicted paper from Primrose Kitten for 2023. So you have an hour and a half to do this paper in the exam, but for now just allow yourself the time to really understand how to do each question, and anything you get stuck on I am here to help you. Okay, so for this question here we're given a reaction and we're given a selection of enthalpy changes and asked to find the enthalpy change of this original equation. It's asked very differently to normal. It isn't a traditional Hess cycle, it isn't a traditional bond enthalpy question, but we need to have a think of how we can use the information that we're given here to piece together to work out the enthalpy change of the reaction in the question. And so what I would suggest that we do in this case is just try and puzzle it together. Think, how can I use these reactions to compose the original one? So let's have a look at this then. So I can see that we start with this substance here, CH4. I can see that as one of the reactants of our main overall reaction. So what I would suggest that we do is initially just write down that reaction here. And you're going to see what I'm doing as I do it, okay? So now I can see that I also need some water. And more specifically, if we have a little look over here at the products, I need 3 H2s, okay? Now I can see that there's some H2s here, but there's just one H2 there. And of course that is on the reactant side. What if we were to flip around this reaction though, and instead have water makes H2 and a half O2? And because we need 3 of these H2s, let's try timesing this by 3. Okay, so then we would have 3 waters make 3 H2 and 3 halves oxygen. So next, the last thing, if we look at that top equation there, I can see I've got carbon monoxide. I can also see that there's a carbon monoxide there as a product again. So rather than it being a reactant, it's a product. So let's again have a go at flipping this one around then, okay? So I'm going to have CO2 makes carbon monoxide and a half oxygen. So I've sort of flipped that around now so that I have the reactants and the products in the right place. Now you may be thinking, why on earth have I done this? But I bet now if we combine these 3 equations, we're going to have that original equation that we wanted. So I can see there's a carbon dioxide on both sides, so I'm just going to cancel those out. I can see there's 3 waters on the reactants and 2 on the products. So I could cancel out 2 of those and just be left with 1 reactant. Then on the oxygens, I can see I have 2 oxygens on the reactant side, and actually in total I also have 2 on the product side, which means that they can just cancel out. And see, if you have a look now at what we haven't cancelled out, actually leaves us with exactly what we wanted. It's the CH4 plus an H2O makes a CO and 3 H2s. So what is really important here then is we have found a way to put together these reactions to be able to get the reaction we wanted. And each of these reactions are associated with a certain enthalpy. Now, the original one was minus 937, and we did nothing to change that first equation that we wrote down. We didn't move it around, we didn't flip it around, we didn't multiply it by anything. This second equation, on the other hand, we did flip this one, didn't we? We flipped it and we also times it by 3. Now the flipping is going to change the sign of that to a positive from a negative. And it's going to be times by 3 because we times the equation by 3. So instead of 3 times minus 297, we're just going to do 3 times 297. And this last reaction here, again, we flipped this reaction to get the reactants and products in the right places, but we didn't times it by anything. So we're going to reverse the sign again, and this time make it positive 257. So now if we take all of these numbers and simply add them together, we will get our enthalpy change. So if we tap this away into a calculator, I get an answer of 211. And that there will be our answer, 211 kilojoules per mole. Quite a tricky question in many ways there. Really, really different way of looking at it, which I think makes it so valuable for us to have a go at now together, rather than the first time you see it being in your exam. So I think you should be really happy that you've seen a question like that now, because hopefully if you see something similar to that now, you're going to know exactly how to handle it. Good job. Okay, let's have a look at the next question. So for this enthalpy question, we're given the bond enthalpies of several of the bonds that pop up here, but not all of them. And we're asked to find the bond that's missing, the OH's enthalpy. So first things first, we don't even know what delta H is in this question, but we can work it out using some of the other information that we know. Normally in these questions, we are told that the delta H, so the enthalpy change, is equal to the enthalpy of the bonds broken minus the enthalpy of the bonds made. So in that case here, if we have a look at what we have, I always like to draw out the molecules, especially for these slightly harder ones. I've got my methanol. I know I've got 1.5 oxygens, and then I have got CO2, and I've got 2 waters, so 2 H2Os. So that just helps me when it comes to writing down all of the bonds that get broken. So I can see out of the ones that get broken, I have got 3 C to H bonds. So I'm going to say that delta H is equal to 3 times the C to H plus this C to O bond. So plus just one of these C to O bonds, and then plus this other O to H bond. But we don't know what O to H is, but we will just write that down for now and worry about it later. And then that's all of the bonds in the methanol, but then we're also going to add on there as well. So I'll just make some space here still. Add it on for the oxygen, and I know that I have got 1.5 of the O to O's. So that in total is all of the bonds that I'm going to break. So now I'm going to subtract the bonds that we make. And looking at this formula, I can see that I am going to make 2 of the C double bond O's and 4 of the O to H's. So that will give us that change in enthalpy. So what I would do now is I would be very careful with this now, and I would substitute in all of the values that we know. And I'm not going to rush this because this is essentially some algebra that we're doing. We don't want to rush it. So we're going to get that delta H is equal to 3 times the C to H, so 3 times 413, plus the C to O, which is 358, plus an OH, which we don't know what it is, but plus 1.5 times 495 for the oxygens. And then we're going to subtract 2 times the C double O, so 2 times 799, plus 4 of those OHs. And what I would do now is I would try and simplify this as much as I can. Okay, so 3 times 413 leaves me with 1,239. I know that I also have the plus 358, and then I also know that I have plus 1.5 times the 495, which is going to give us 742.5. So then I would add on the OH, and then I subtract 1,598 minus the 4 OHs as well. Be very careful of that minus with this plus, which make this negative here. Okay, so this is something now that we can sort of tidy up and simplify a bit. So if I put into the calculator now all of these numbers, so ignoring the OHs, if I substitute all of those into the calculator, then I end up getting 741.5, and then combining all of those OHs, I have an OH minus 4 OHs, so I have minus 3 OHs, and that is going to be what our delta H is equal to. But we're kind of reach a dead end here, don't we? Because we can go a step further. You know, we need to know what delta H is. So we need to ask ourselves, well, how can we do that? What other information do we have? So if we go to this very first line in the question, we're told the mass we have of methanol, and we're told the heat given off by that. And we can use that to calculate the enthalpy change. Because remember that delta H is equal to Q over N. So this is a complete combustion, so we know the enthalpy change will be negative because it's an exothermic reaction. We know that Q is 217.7 kilojoules, but we don't know the moles yet. If we work out what the MR is of the methanol, then we can work out what the moles is. So the MR will be 12 plus 3 plus 16 plus 1, and that ends up giving us an MR equal to 32. So the moles of the methanol will be 10.5 divided by 32. And that leaves us, when we put that into our calculator, with an answer equal to 0.328125. So the enthalpy change here will be 217.7 divided by 0.328125. And I end up getting an answer now equal to 663.5 kilojoules per mole. But of course that has to be negative, because in this case here is an exothermic reaction due to that complete combustion. So we're very nearly at the end of this. It's quite a lot of work for those 4 marks, but sometimes this is the way a question goes. So now let's finish this all off. So we said, didn't we, that 741.5 minus 3 OHs is equal to the enthalpy change, which we've just said is minus 663.5. So now we can give this a good rearrange to get a value for OH. So the first thing that I would do is I would subtract from this 741.5, and that leaves me with minus 3 OHs is equal to minus 1,405, if we round that to the nearest whole number. And so if I now divide that by minus 3, I will get the enthalpy value for just an OH, and that is going to be 468.3. And so the bond enthalpy for OH is going to be 468.3, or you could just say 468 to be consistent with the other answers, and the units would be kilojoules per mole. Whew. Seems really complicated, that, but really if you strip it back, all we had to do was use 2 of the common equations for enthalpy, one of them being that enthalpy change is Q over N, and also the fact that we can work out the enthalpy change by working out the sum of the bonds broken minus the sum of the bonds made. But that was really good, we got through it in the end. Let's have a look at the next question then. So here we're told that the bromine test can be used as a qualitative test to determine the presence of unsaturation in 2-butene. And what unsaturation means is the presence of alkene bonds. So we're asked here to draw the structure of the E and Z isomers of 2-butene. So the very first thing that I would do is I would draw out butene, not worrying yet about whether it looks like an E or a Z isomer, and we'll just start there. So initially we know it's got 4 carbons in a row, and because it's butene, we know on the second carbon we have a double bond. So if we were to sort of fill this in just in a normal boring diagram, it looks like this. So next though, we need to translate it into this E and Z stereoisomers. So what I'd always recommend with these that we do is we draw the central C double bond C and make it look a little bit like ethene, whereby we can circle off the groups attached to each of those carbons of the carbon double bond, and then sort of attach those in the relevant places over on our molecule. So here we go, this is how I have redrawn it. The only reason why I do that is because I feel like it's much more visually understandable to be able to say which is the E and Z isomers. So E isomers are essentially trans isomers. So that will be when the same group is on opposite sides of the CC double bond. So what I've just drawn here is actually the E isomer. So I will fill that in the space that they want. And then the Z isomer is the same as the cis isomer. And so that is when we have them on the same side of each of those carbons. Doesn't matter if you do the H's on the tops or bottoms, it will work out the same either way. Next, we want to state the meaning of the term stereoisomers. So this definition, not only is it good to know for these questions, but also just for your understanding of what a stereoisomer is. So what a stereoisomer is are a set of molecules that have the same structural formula, but whose atoms are arranged differently in space. So here, if I was to define stereoisomers, I'll write it over here for you. I would say that they are molecules with the same structural formula, so molecules with the same structure, but with a different arrangement in space. And those are your 2 points that you need to know to be able to get these definition questions correct for a stereoisomer. And at this level, we only really know about cis, trans or EZ stereoisomers. In the second year, if you're a student that's currently in the second year of A-level, you'll be familiar with optical isomers as well, which are also an example of a stereoisomer. But that's our perfect definition for what a stereoisomer is. So now, using the curly arrow model, describe the mechanism for the reaction between Br2 and this 2-butene. And it doesn't matter which version we use, it's not going to matter. So, first things first, I will draw one of our iterations of the butene. And then the next thing I will do is I'm going to show bromine sat next to it, but polarised. And remember that this CC double bond is a region of high electron density, so it is able to do that. So Br minus, Br plus. Now what we want to do is to show the movement of a pair of electrons from this CC double bond to the delta positive bromine, and from the bond between the bromines to the delta negative bromine. And what that will then do is it's going to form an intermediate where we have a carbocation, and we also have now formed a bond between one of these two carbons and the bromine. We've also, due to the movement of the pair of electrons between the two bromines, we have formed a negative ion. So the final step of this is the movement of the electrons in that bromide ion towards that carbocation. And that forms that final bond that we need to have finished this mechanism. So there we go. Pretty perfectly done, I think. Lovely. And the great thing is that particular mechanism is going to look the same whatever alkene is needed. Remember, all the groups coming off of it, they're not going to impact on this basic structure that we have every time we see one of these electrophilic addition mechanisms. Perfect though, let's see what the next question is. Okay, so we're told that nickel is a metal in the transition metal block of the periodic table, and we're asked to give the electronic configuration for the nickel 2+ ion. So here what I would recommend that we do is we start off with saying, okay, for 3.1 here, what would just nickel be? That's always how I would start this. How would just nickel be? And nickel would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. And then when we get the nickel 2+ ion, what we end up getting then is we lose electrons from the s subshell. So these two electrons will leave. So lost these electrons. So we're just left now with 1s2, 2s2, 2p6, 3s2, 3p6 and 3d8. And that there will be the electronic configuration of the nickel 2+ ion. Okay, so next we're told that nickel has an atomic mass of 58.693, and we're told to explain why. And at first that question might seem a bit odd, but really all that's getting at is, why is it a decimal? You know, we learned that atomic masses should be, say, the sum of the protons and the neutrons, and you can't have 0.693 of a proton or a neutron, can you? And so what we want to explain here is the fact that this atomic mass is actually the average mass of all of the naturally occurring isotopes of nickel. So that is what we would write down. The fact it is the average mass of all of the naturally occurring isotopes of nickel. Perfect. So in the next part, we're given a reaction between zinc and nickel nitrate, and we're asked to give the oxidation state of nickel in nickel nitrate. So the way that I would do this is I would use my knowledge of the fact that the nickel ion is NO3 minus. And I would tell myself, well, I have 2 of these NO3 minus ions, which must mean that overall the charge of the nickel, and that tells me that overall the charge of those 2 nitrate ions is going to make -2. Now, overall nickel nitrate has a 0 charge, doesn't it? It's not a charged compound. So that must mean that nickel's oxidation state has to balance with the -2 that we have coming from the 2 nitrates. So nickel must therefore be +2. So then we're asked to give the equation for the oxidation reaction and then also for the reduction reaction. Now, it's important that we remember that in an oxidation reaction, the oxidation number increases, whereas in reduction, a bit like the word reduction implies, the oxidation number goes down. So that's sort of how we want to distinguish between these two things going on. Now, out of these, nitrate is unchanged. We have a nitrate on the left and we have a nitrate on the right. So that isn't going to really take part in these. But what we will have is we're going to have nickel 2+ becoming nickel, and we're going to have zinc becoming zinc 2+. So just to show you where that's coming from, so your nickel 2+, obviously that's coming from the nickel nitrate like we just said, and it makes a nickel. And then on the other hand we have a zinc and we make a zinc 2+. Now these two little equations that I've written down haven't been balanced yet. We will need to add in a couple of electrons. So now they're balanced. Now looking at these two reactions, we can distinguish between them and say which of them has been oxidised and which one has been reduced. Either we can use what I've just said about the oxidation number. So you can see that here we have an oxidation number of 2+ for nickel 2+ and 0 for nickel. So the oxidation number has decreased. So this has been reduced. Whereas on the other hand, zinc is 0 and it's gone up to 2+. So that equation there has seen zinc be oxidised. But alternatively, we could also look at it via oil rig. And remember, oxidation is the loss of electrons, and we can see that has happened here. And we can also see that reduction is the gain of electrons, and you can see nickel 2+ has gained electrons, so it has been reduced as well. So 2 different perspectives that we could use there. So for 3.4, the half equation for the oxidation reaction is going to be zinc goes to zinc 2+ plus 2 electrons, whereas the half equation for the reduction reaction will be nickel 2+ plus 2 electrons makes nickel. So that's that one all finished. Okay, so now we have another electronic configuration question here. And here we're asked to write the electron configuration of the As3+ ion. So the way that I would do this is I would have a little look at the periodic table, and I would start just by writing down the electron configuration for just As, just for arsenic. And I can see that that is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p3. So now, if we want to form the As3+ ion, we need to lose 3 electrons. And the 3 electrons that will get lost in this case will be these 3 p orbital electrons. So therefore As3 plus is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And remember that the way that we can work this out is by taking the number of electrons that it has, adding them together until you reach the electron number of this specific atom or ion. Remember, ions either gain or lose electrons. In this case, because it was As3+, it had lost 3 electrons, and that is what we showed here. But the initial format, obviously we have to learn that it goes in this 1s2, 2s2, 2p6 sort of rhythm to it. But then it's sort of thinking, well, how many electrons does it have? And As has 33 electrons. So when we sort of added up all of these, it ended up getting us to that 33. Okay, so next we're asked to state the meaning of the term first ionisation energy. And this is a great definition to learn. It is really straightforward and it's a great rhythm to this definition. So 4.2. So the definition of first ionisation energy is it is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. Now that is the definition, that is the fullest definition you could give, the most perfect one, and I would recommend you learn that because you can adapt that to then learn the second ionisation energy, the third, the fourth, whatever they want to spring at you. So let me write that down for you. Okay, so it is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. So the really, really important things to state in this question, obviously that it's the energy required, but it's particularly that reference to gaseous and the 1 mole. Okay, those are 2 really key things because ionisation energies, they are explicitly about gaseous ionisation. It will be completely different numbers if it wasn't for that. So it has to be gaseous and it's all about 1 mole. I think most enthalpy changes that we get are the energies per unit mole. And ionisation energy is all about telling us how much energy we need to remove electrons from each atom in that 1 mole of gaseous atoms. But that's really good. So now for 4.3, we want to give the equation for that first ionisation energy of arsenic. And like we mentioned, the importance of that word gaseous, whenever we do this, we need to include those state symbols, just like it has said in this question. So here you'll find that that definition can help us to do this. So we're going to have these gaseous atoms, and we're going to remove an electron from each of them to form 1 mole of gaseous 1 plus ions. So see, we've just directly translated that definition into putting it into practice there. So in question 4.4, we're asked to explain why the first ionisation energy in selenium is actually lower than that of arsenic. Because as you can see, the general trend here through this period is that they're increasing. So this is quite a common question, sort of really testing your depth of knowledge of ionisation energy. And the way that I'm going to explain it here is going to be by doing my little box diagram for the electrons in that p orbital. Okay, so arsenic, AS has 3 electrons in that subshell. So arsenic will look like this. 3 electrons, great, okay? But selenium, and I'll use a different colour for this, selenium actually has 4 electrons. So it's still got those first 3 the same, but now we've got a 4th electron. So this is the really, really important thing to talk about here, okay? So we can say that in selenium, we have a spin pairing occurred. And that's the first time that occurs in this period. So we've got spin pairing has occurred. And that is what we call this occurrence. where for the first time we've got 2 electrons in that same orbital. So if you don't like that wording of spin pairing, you could say that for the first time we are removing an electron from an orbital that contains 2 electrons. Okay, so the important thing here is that when we've got 2 electrons in that one orbital, they don't want to be there together. Think of 2 of you sitting on a bus. First opportunity for a free seat, you're off, right? You don't want to be sat next to someone you don't want to be. Electrons are exactly the same, only they've got the additional factor of the fact they are both negatively charged. So actually, they are repelling each other, which means that they are more eager and more easily separated. So as our final thing to mention here, I'm going to say that there's an increase in repulsion and therefore it's lost more easily. So increased repulsion, so electron removed more easily. So let's just take a minute just to recap that. So arsenic compared to selenium, arsenic only has 3 electrons in the p subshell, whereas selenium has 4 electrons in the p subshell. Because of that, what we get with selenium is we get 2 electrons in one orbital. 2 electrons in one orbital are going to experience repulsion, which means that those electrons are more easily removed from the atom. And that is why we have a lower first ionization energy for selenium than arsenic. Okay, so now we need to explain why the first ionization energy of rubidium is lower than that of krypton. And the thing to do is have a little look at your periodic table and observe where rubidium is compared to krypton. And you can see, although that there's only 1 extra proton, it is in the next shell. And so because it's in the next shell, it means that there is a bigger distance from the nucleus and there is more shielding. And as a result, it's going to take less energy to remove it because there's already less attraction between that electron in the outer shell and the nucleus due to that increased shielding and that bigger distance from the nucleus. So our answer here that we would write down is that in rubidium, the electron is further from the nucleus, and this is because the electron is in a new shell. Perfect. Okay, so 4.6. A reaction was performed using 96 grams of arsenic and 5.29 times 10 to the 24 molecules of oxygen to form diarsenic trioxide. The chemical equation is as follows. So now we need to say, well, which of these reactants is the limiting reactant? So having a look at this, first let's have a go at writing out the formula because I always like to sort of annotate it and write beneath it any of the facts that we know. So we know the mass of arsenic, don't we? We know that there's 96 grams. So if we have a little look at the periodic table there, we can see that the MR of arsenic is 74.9. So we could work out how many moles we have of arsenic. We could say, using the fact that mass over the MR is the moles, we can say that we have 1.28 moles of arsenic. So when it comes to the oxygen though, they didn't tell us how many moles and they didn't tell us the mass either. What they told us instead was the number of molecules. And we need to remember that if we know the molecules, we can work out the moles by dividing it by Avogadro's constant. So if we do here, the moles equals the molecules over Avogadro's, let's work that out then. So 5.29 times 10 to the 24 over 6.02 times 10 to the 23. So tapping that away into the calculator, I get 8.78 moles. So we've got all the information we need now. We know the amount of moles of the arsenic and we know the amount of moles of the oxygen. So to determine which of these reactants is the limiting reactant, what we want to do is to use this ratio of 4 to 3 between the arsenic and the oxygen. And we could say, okay then, if I have 1.28 moles of arsenic, how many moles of oxygen would I need to do that? So if in that ratio 4 is equivalent to 1.28, We could work out what one part of that ratio is by dividing that through by 4. And that leaves us with 0.32. And then 3 parts of that ratio would give us 0.96 moles. So in theory, if we had 1.28 moles of arsenic, we would only need 0.96 moles of oxygen. And actually, as you can see here, we have a lot more than that 0.96 moles. So therefore, I would say that in excess is our oxygen, and so our limiting reagent is going to be the arsenic. So that there would be our conclusion to that question. So I hope that that made sense. So there we needed to get the moles of each of them, work out which one we have in excess, and then the other one is the limiting reagent. Perfect. Okay, so this question here wants us to work out the relative atomic mass of krypton. So they've given us this data. The way to work out relative atomic mass is we take the mass of each individual atom, times it by its abundance, add them all together and divide by the percentage. So in this case, we're going to have 82 times the 12 for this. And then we're going to add 83 times 12. And then we're going to add 84 times 50. And then we're going to add 86 times 26. And once we've added those all together, we're going to divide it by 100. And we would certainly expect our answer to be somewhere between 82 and 86. It's not going to be any more or less because that is the data that we've used. So tapping that away into the calculator, I get 84.16, which once we do it to one decimal place is just 84.2. Perfect. Okay, so now we need to give the equation that occurs when the first ionisation energy of krypton is measured using the mass spectrometer. So this is going back to what we said in an earlier question, the first ionisation energy is. So to do that, remember, it's when we remove an electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. So that there will be our answer. And it's a 2-mark question, and you can see you're getting your mark for that correct reaction, sort of the correct symbols in the correct place, and then another mark for the state symbols. So here we've got a nice empirical formula question, always a popular question. First, we need to just find the empirical formula of this Z, which we know has a composition of 55.8% carbon, 11.2% hydrogen, and 33.0% chlorine. So I like to do these by filling in a little table where I have the percentage mass, I have the MR of each of them. So I know carbon is 12, hydrogen is 1, and chlorine is 35.5. And then I calculate the mole ratio of these, which is basically just the moles, but because it's not the actual mass, it's just the percentage by mass, we can't actually strictly call it the moles. But I do that, and this is why I love laying it out in this way, just by dividing them respectively by each other. So here, if I do 55.8 divided by 12, I get 4.65. For H, I have 11.2 because we're just dividing it by 1. And then 33 divided by 35.5 gives me 0.93. So now, to work out the empirical formula of this, I now want to divide by the smallest. Because what I want, I have a ratio at the minute, I want to get the simplest whole number ratio. So if I divide each of these through now by 0.93, hopefully we are going to get a nice whole number ratio. So if I do 4.65 divided by 0.93, I get 5, brilliant, a nice whole number there. If I do 11.2 divided by 0.93, I get 12. And of course I'm going to get 1 when I divide 0.93 by itself. So now we can put all that together to say that the empirical formula is C5H12Cl. We don't need to write the little 1 next to the Cl because just like in maths, whenever there's just 1 of something, we just don't write it. Okay, so now we need to find the molecular formula of Z. And the important bit of information they've given us here is that the relative molecular mass is 107.5. So the way that I would start is by working out what the MR is of my empirical formula. Because ideally what we want to do here is work out, well, how many of these empirical formulas fit into the molecular formula. So here I'm going to do 5 times 12 plus the 12 plus a 35.5. So this is from the carbon, this is from the hydrogen, and this is from the chlorine. So tapping that away then, I get left with an MR of 107.5. And notice there, that is exactly the same as the MR of this compound Z, which must mean that the molecular formula is actually just the same as its empirical formula. So it's going to be C5H12Cl. Okay, so for 5.3, a student allowed compound Z to react with sodium hydroxide to produce compound Y. Write the balanced equation for the above reaction. So what we need to know here is what happens if we react a haloalkane with a hydroxide. And what's going to happen is a substitution reaction where we get NaOH plus this C5H12Cl. And what is going to happen is we will get NaCl, but we will also get the alcohol pentanol. So that there will be our reaction. Now they ask us what type of mechanism occurs. Now remember, mechanism isn't the same as what type of reaction occurs. Mechanisms are talking about the curly arrows, and they'll normally refer to, say, nucleophilic substitution or electrophilic addition at AS. So in this case, what we have is a nucleophilic substitution. So that will be our answer for this one. Okay, so the student calculated that the maximum yield of compound Y was 6.5, but his actual yield was 3.2. Calculate the percentage yield of this reaction. So this is quite a nice percentage yield one, because for percentage yield, it is like the actual over the expected or theoretical, which in this case is going to be that maximum yield, and then we times it by 100. So in this case, it's going to be 3.2 over 6.5, and then times by 100. So if we put that into our calculators, what do we get? So here I get an answer for a percentage yield of 49.2%. So in this question, we've got 5 test tubes labelled A to E that contain the following solids. So we've got ammonium carbonate, magnesium carbonate, ammonium sulfate, ammonium nitrate, and barium carbonate. And we've done a selection of tests which are going to help us to distinguish between them and identify them, okay? So here, what I would probably do if I was in an exam is I would look through these and ask ourselves, well, what jumps out to me the most? So if we look through these one by one, so which of these, when we heat it, might break down to give us 3 products which are in a gaseous state? So looking through these, I can see it's not going to be one of the metals. It's not going to be magnesium or barium because they're not going to make a gas. So it's likely going to be one of the others. And I would say that the most likely one will be the first one, because that ammonium carbonate, when we heat it, we could break it down into some ammonia, some carbon dioxide, and some water. So I would say that in all likelihood, A is that first substance, ammonium carbonate. So looking through these, I can see a couple of oxides that get made. And oxides often form from the thermal decomposition of metal carbonates. So I would say out of these two, C and E, that's likely to be the magnesium carbonate and the barium carbonate. So we need to say, well, which of those is going to give us a white oxide which reacts with water to form a weakly basic solution and a colourless, odourless gas, whereas the other one, it forms a hydroxide that reacts with sulfuric acid to form insoluble sulfate. Now, for me, obviously they're both going to form hydroxides through this decomposition. What we need to know here, though, is which one forms this insoluble sulfate, so magnesium sulfate or barium sulfate. Out of those two, the insoluble sulfate will be barium sulfate. And remember, that's actually the test for sulfate ions, the addition of barium substances such as barium chloride. So E, I am going to say, is going to be barium carbonate. Whereas that leaves us with C being magnesium carbonate, because that is the other metal carbonate which will thermally decompose to form white oxides. Okay, so now we've got a couple of options here, haven't we? We have got one which forms a colourless, pungent smelling gas that turns damp litmus paper blue. So that means that ammonia is formed. Whereas in the other one, we've got a colourless, tasteless, non-toxic triatomic gas with a linear structure and water vapour. So out of these two, we need to think, well, which of these is going to form like ammonia? And I would say that out of those two, the one which will form ammonia is going to be the thermal decomposition of ammonium sulfate, which when that is heated is going to break down to leave us with some ammonia and some sulfuric acid. And that there is how we're going to get this gas, this ammonia gas, which is going to turn that damp red litmus blue. So on the other hand, in D, when we've got this colourless, tasteless, non-toxic triatomic gas, well, nitrogen compounds are often non-toxic. We have them all the time, like nitrogen dioxide, nitrogen monoxide, and so on. In this case, it makes sense that if we've got this gas, which we know is non-toxic and colourless and tasteless, that it is likely going to be some sort of nitrogen oxide. So if we have here this ammonium nitrate, then when we thermally decompose this, we can end up making N2O and water. And we know that N2O is going to be like a non-toxic triatomic, so it's made up of 3 atoms. So we have here what we wanted. So quite a challenging question, that one, so don't worry if you're not sure of it. Obviously there was a lot of knowledge needed there and a lot of sort of understanding as to how these things might react. So A, we said, was ammonium carbonate. B, we said, was ammonium sulfate. C was magnesium carbonate. D was ammonium nitrate. And E is barium carbonate. So now here they want us to write those balanced chemical equations, and for most of those reactions I'd already mentioned them, but let's just recap them now. So when we do the thermal decomposition of ammonium carbonate, we end up breaking it down to form 3 gases. We got ammonia plus carbon dioxide plus water. So that is much like many carbonates. We end up breaking them down to form these carbon dioxides and waters. So then we have ammonium sulfate, which we said will thermally decompose to form some ammonia and some sulfuric acid. On the other hand, we've got magnesium carbonate, which, and this is quite a common thermal decomposition, we get magnesium oxide and some carbon dioxide. Then when we had ammonium nitrate, when we thermally decompose that, I got N2O plus water. And then finally, barium carbonate, using exactly the same process as magnesium carbonate, another group 2 carbonate. We will thermally decompose that to form barium oxide and carbon dioxide. Okay, so here we want to write a balanced chemical equation for the formation of insoluble sulfate in test tube A. So remember we said, didn't we, that when the resulting hydroxide reacts with sulfuric acid, we know that we get this solid substance, this insoluble substance. And so here we need to write down that balanced equation for that. So I previously mentioned that that insoluble substance that we make is barium sulfate. So we know we're starting from a hydroxide. In this case, that will be BaOH2. We need to have the OH2 because of the fact that barium is in group 2. And then we add there the sulfuric acid. Don't forget your state symbols. Both of these are solutions, they're both soluble. And the reason why we need those state symbols is because we're making something insoluble. We're making barium sulfate, which is a solid. And we also make 2 waters as well, which are liquid. So that there is our balanced chemical equation for the formation of that insoluble sulfate in test tube E. So the gas which is evolved in test tube A and B can act as an oxidising agent as well as a reducing agent. Write the balanced chemical equations to explain the above statement. So this question here is a real stretch question, okay? First thing that we need to notice is, well, what is this gas that is evolved in both test tube A and B? And that is going to be ammonia. So what they're saying here is that ammonia can act as an oxidising agent and a reducing agent. And we just need to come up with some examples of when that might happen. So one example could be when we have a metal reacting with that ammonia. Okay, so imagine if we had, say, some sodium and we're reacting it with the ammonia. That reaction will end up making some Na, NH2, and H2. So here you see in this particular reaction, what has happened is that ammonia has acted as an oxidising agent because it itself has been reduced, and by being reduced there, it has oxidised the sodium. We can see that because if we look at this, we go from an oxidation number of 0 up to +1. So we can clearly see that it has been oxidised, which means ammonia has been the reducing agent. So that would be what I would write as my example for it being an oxidising agent. Of course, you could use other metals as well, that would work as well. So then for it being a reducing agent, an example of that is if it was to react with, say, chlorine or oxygen or something along those lines. So if we were to take chlorine, and react that with some ammonia, what we would end up making is some HCl and some nitrogen gas. So if we balance that quickly, we can see it's nicely balanced. But the key thing here is that that chlorine has gone from having an oxidation number of 0 when it's in the form of Cl2 to being -1 in HCl. So there the oxidation number of chlorine has reduced, which means that the chlorine has been reduced and therefore the ammonia has acted as a reducing agent. So like I say, really quite a stretch, that particular question, but don't worry at all if you found that challenging. You know, some of the questions are that little extra stretch, so just try and absorb what I'm saying here, and hopefully you'll be able to have a go if you ever saw that come up again. Okay, so this question is based on the substances A, B, and C, and we're asked to name substance A. So here, the very first thing I would potentially do is draw it out, but in fairness, it's probably clear enough as it is. I would draw a line through the longest chain of carbon atoms. And here I can see that I have 4 carbon atoms in a row. And I can see that amongst those I have a butene because I have 4 carbons. So I can say that I have but1ene there because if we number those carbons, I can see that the double bond is attached to the first carbon. And then I can also see I have a methyl group, and I can see that that is branching off of the 3rd carbon of that chain. So I can say that here I have 3-methyl but1ene, and that there is going to be the name of our substance A. So now we're told that that same substance A reacts with HBr, and we're asked to draw the structure of the major product for the reaction of A with HBr. So I would start now just by writing it in a more familiar format. So I'm going to write it like this. I can see that there's 2 H's coming off of the right carbon of that double bond, and on the other side I have an H coming off of that second carbon, and also I have a CH3 2. Okay, so there I can see I've got that branching. And the important thing here when it comes to determining which is the major or the minor product is what position is the bromine going to attach to? Is it going to attach to this carbon here, which has this group attached to it? Or will it attach to this carbon which doesn't have any groups attached to it other than just hydrogens? And the answer here is that in the major product, the bromine or the halogen, whatever halogen it is going to attach to the carbon of that CC double bond that has the most other groups attached to it other than hydrogens. So in this case here, my major product is going to have the bromine attached to this carbon, which has the CH3 attached to it. And on the other carbon, that's where the hydrogen will go. So this here is our major product. If they also wanted the minor product, I would just reverse this bromine and this hydrogen, and that would give us our minor product as well if we needed it. Okay, so substance B can be polymerized to form the polymer X. Identify the polymer X. So here they just want us to identify it, which means they just want us to name it, basically. So the first thing to do is to name what that monomer is that they have, okay? And that monomer would be phenylethene, okay? So the polymer version of that is going to be polyphenylamine. So just make sure that you're confident in naming substances like B. So phenylethene, so that's called phenylethene, and so the polymer would just be polyphenylethene. So for 7.4, we're told that substance C can be polymerized to form polychloroethene, and we're asked to show a balanced equation for this. So when it comes to the monomer of this, that is just chloroethene. And when it comes to writing a balanced equation for the formation of a polymer, we want to put a little N in front of it. And then what that will become is something where we break open that double bond so that it has nice little open arms. Everything else looks exactly the same, but we're going to add in some brackets around it and a little N down on the bottom right hand corner. And so that there is a formation of polychloroethene from simply chloroethene. Perfect. So here we've got waste polymers, and we're told that they can be disposed by combustion after their useful life. But we're told to give one problem with the disposal of polychloroethene by combustion. So it's important that we know that due to the presence of chlorine in this particular polymer, when we burn it, we release HCl gas, and that can be problematic because that gas is toxic. And that is the main problem that we have with the burning of polychloroethene. So now we're asked to construct the balanced equation for this combustion. So here we're combusting 1 unit of polychloroethene. Now we've already said, haven't we, that it releases HCl. So HCl is going to be one of the products of this combustion, as well as other very common substances that forms when we combust things. We're also going to make CO2 and also water. And the thing that we always need, whatever it is that we're combusting, is oxygen, okay? So now we've got the general framework there, we can have a go at balancing this now. So I can see that I have 2 carbons in my polychloroethene, or in 1 unit of it. So that means I'm going to balance the CO2 with a big 2 in front of it. So in terms of how many hydrogens there are, I can see that there's 3 hydrogens in this unit of polychloroethene, and there's 3 units over on the other side too. So I'm actually happy that the chlorine, the carbon and the hydrogen are all balanced right now, but the oxygen probably isn't. If I look over on the right hand side, I can see I have got 4 oxygens in the 2 CO2s, and I've got 1 in the water. So I've got 5 oxygens in total on the product side, which means I need to have 5 oxygens on the reactant side. That must mean then that I need 2.5 O2s, and that is now balanced. Finally, for the last question of this paper, we're asked to describe 2 ways that scientists can reduce the environmental impact that disposing of polymers causes to the environment. So a few options that we could say here, there's quite a few. We could say that we can crack polymers, because that can break it down into smaller chunks that maybe are easier to get rid of or maybe to reuse. Better recycling can be good. That would be another option. Other options would be things like improving atom economy so that only the thing we want is made. Maybe using some development of other types of polymers such as biodegradable polymers or plant-based polymers or photodegradable polymers. All of these things will break down much easier than we currently have for the traditional crude oil polymers. But that's really, really good. And that is the end of the paper. I hope that you're feeling a bit clearer on some of those questions that you got stuck on. And I hope you feel ready to try another paper. And I'll see you soon, okay? Bye, good luck.
Ouch! This is why in some videos I've explained scratches.